So I'm going to start off just kind of talking about robotics in general, and then get into hopefully how this is somehow relevant to you all. So first of all, who has played with a robot before? Okay. So a few people. I've got a 2-year-old, and we're obviously looking at toys, and now there's more and more geeky toys for kids. It's great. And part of the reason for that, things like toy robots, is because robots are getting so much cheaper now. That something that would have cost $100 can now be $20, or something that was $20,000 might now be $1,000. So the biggest challenge, biggest challenge in robotics is figuring out what the world is around you. And figuring out, okay, how do I perceive the world? How do I make sense of all of this data? And then I need to do something with it. I might need to figure out where I am. And then if I know where I am, I might need to figure out where I need to go or what I need to do. And then I probably need to figure out how to actually change my motors. So once I know, I want to go somewhere, then I need to set the voltages on my different actuators. So there's lots of different levels of abstraction you can think about. So when you talk about robotics, it's really a ton of different disciplines. I think about it mostly from the computer science side, but there's really work from the computer engineers, the electrical engineers, the mechanical engineers, all of that going into a physical platform that works robustly. So a lot of the time, you can do something either with a really fancy, complicated algorithm like balancing. Getting a humanoid to balance on 2 legs is actually pretty hard. And you can use these really complex algorithms to do that, or you become friends with a smart mechanical engineer and they come up with this way of getting the robot to balance that doesn't take a whole lot of smarts, just because they've come up with some kind of mechanism that's able to do it. So it's good to have friends in lots of places. And that's also true because I've recently been doing stuff with psychologists and sociologists looking at human-robot interaction. So right now, a lot of robotics is you have a robot, it goes and does its thing, and then comes back to you. And what we want to talk about today is more, how does the robot interact with a person, right? So if we're thinking about healthcare, it's not just going to be the robot doing things for the person, it's going to be asking the person what you want to be done, helping the person in the right way. So just so I can show off some of our videos, here's one of the projects we have where we have multiple UAVs. So we saw them just take off now, and now you can see they're doing this coordinated lawnmower pattern. So you can think of anytime you have one robot, it'd be cooler if you had multiple robots doing the same thing. Again, they're going to take off over here and then start going across. And you can kind of see the shadows. Sorry it's so small. One thing I won't really be talking about today is multi-robot stuff. It turns out getting 2 robots is much more than twice as hard as getting 1 robot to work. So there's lots of interesting challenges there. The other thing that I wanted to point out is UAVs or drones are really hot now because they're so cheap and capable. Now we can buy flying robots for under $100. How cool is that? And then the autonomous ones are more like, $200, $250. So we have drones that are doing a lot of things. Some of the motivation is for agriculture. The other project that I just wanted to mention is kind of cool, there we go. So, stop playing. It could either have sound or motion. So this is a bin dog. So what this is it's a robot that's going to go around an apple orchard and then pick up bins full of apples that weigh up to 800 pounds. So this thing goes autonomously and figures out which row do I want to turn into, and then turns and then starts going into the row. What makes this interesting is if you've been in apple orchards in the Pacific Northwest, is that there's these really regular lines of trees. So the bins are just a little bit narrower than the aisles. And our design has to be just about as wide as the bins. So we're going down these aisles of trees with about 6 inches of clearance on each side. And we've driven over 15 kilometers autonomously and haven't killed one tree. So that's pretty exciting. We also haven't killed any people, which is also important. But this is an example where we have to take the robot out into the wild. And in some cases, what we're talking about may be easier. So if you have a robot in a hospital, or if you have a robot in a person's home, you might be able to augment it to make it easier. Or you might be able to, make sure there are no stairs, or remove things that might trip the robot. Whereas if you're in a completely unconstrained space, there's so many things that could go wrong. So for instance, a few years ago, the Google car was driving, and then there was a plastic bag that was in the road and kind of fluttered. And the Google car, with very high confidence, knew it was a flying deer. It had never seen a flying deer, but it had also never seen a floating plastic bag. So the robot's got to take its best guess. So that's one of the problems with robotics. You probably heard about all the self-driving car stuff, and there's a lot of debate among AI experts when we'll get to level 4. So fully autonomous, the person can just go to sleep and the car goes. And some people say, oh yeah, just another couple years. And other people will say, no, it's going to be more like 20. So it's interesting when you're in robotics, because 10 years ago we thought we were almost there with the autonomous cars, right? And we still think we're almost there. So maybe we're right this time. Let me show you an example from Boston Dynamics. So this is Boston Dynamics. They're a company out of Boston. Go figure. They're big in military. And then they got bought out by Google. And then Google sold them off. So they are really one of the leaders, and they're all about the cool mechanical engineering. So let me just show you this quick video on some of the reason I want to show you this is give you an idea of what's the current state of the art in terms of what robots can do and look like.
It's a wow moment for robot fans. An impressive new version of the Atlas robot is unveiled. And what steals the limelight? Robot abuse.
Well, it's interesting that America is building robots that people can bully. In 100 years, that scene is going to be in the robot version of Roots. You understand?
And it's not just physical, but mental torture. My hockey stick, wanted and teased, this after doing such a nice job of lifting boxes. Take this job and shove it. I'm out of here. No wonder Atlas fans visualize robot revenge scenarios. And this isn't the first time a highly regarded robot design company...
Freaky looking dog. See, and they're just abusing the poor thing.
Actually, there's a perfectly good reason for this robot abuse. When most robots fall down, they can't get back up. They often have to be carried off for repair. When the new Atlas was forced to faceplant, watch it get back on its feet. Though it stumbles through the snow like Bigfoot, it never loses its balance in uneven terrain. That's a very big deal. Even if one commenter noted, looks like me coming home from the bar last night. Racing engineers are just brutal bullies, lacking any sense of humor. Last year's Christmas greeting from Boston Dynamics, even if their robots aren't laughing all the way. Gino, CNN, New York.
So this is a great example of, well, robot abuse, but of taking the robot out of its normal conditions, right? Because if you have a robot that's just standing there on flat ground, it's not that hard to balance. Getting the robot to walk, that's quite a bit harder. Getting the robot to walk on snow, that's insane. So that Boston Dynamics is doing some really cool stuff, and you can see why the military, for instance, would be interested in this. Let's see, can I click that. Hey, there we go.
We developed a method for generating.
So another thing I wanted to show you was just so here's some examples of quad rotors that can do really impressive things sometimes. But these are examples when things did not go as intended.
We developed a method for generating trajectories to optimally fly through any number of waypoints.
So here's another example of really good control. And it's difficult in part because with these aerial vehicles, there's so much noise.
Dynamic objects.
And one of the reasons they're able to do this is because of these cameras they've got around there. So these are a set of motion tracking cameras. So what they do is they take really high-speed pictures and then think about triangulation. If you've got 3 cameras that see the same object, you can figure out where it is. And in this case, if you have 30 cameras, you can track multiple objects usually with millimeter precision and about 100 times a second. Of course, the problem is you've got to set up all these cameras and put all the cabling in place. So if you have an environment that you can set up and put all of this extra instrumentation there, then you can do lots of cool stuff. And what we're trying to do now as a field is how can we remove these training wheels? How can we go out into the natural world and work even when we don't have these crutches? So again, one of the things that makes robotics hard is going and trying to understand the real world. And it's not just perceiving it and seeing, okay, where is the next closest thing that I can hit, but also understanding. So if you're driving in the car and then all of a sudden you see that you think you're about to run off the road, you have to have some reasoning about, is that really what's happening? Because anything you see, there's a chance that's not actually there. Or is it actually a flying deer? So here's another example of, this is also from the DARPA Robotics Challenge, where they had teams work for multiple years, I want to say 3 years, on multi-million-dollar robots to do these very difficult challenges. And here are some of the results of these robotics experts. So again, these are multi-million-dollar robots that are just not, so they just get a little bit off, and then, or they lose battery. Saw this guy before, tripping up in the sand. He's just having issues. So one of the neat things about this is the robots weren't necessarily acting autonomously. So you could have people in the background that were helping them. So what one of the teams did is, so for instance, when the robot was going to pick something up, what the robot would do is try to decide, okay, how am I going to pick that up? And then people would be watching it back in the van so they could see the robot was thinking about using this trajectory. So they could always jump in and say, no, don't do that. Or they could jump in and tweak the trajectory so that you actually go around something and pick up the can without running into the computer. So there's this idea of, you can have, a robot could be completely teleoperated by a person, so think like a remote control car. Robot could be completely autonomous, or it could be somewhere in between. And that's where a lot of the interesting stuff is happening right now, because autonomy is so hard. It's also really true in the military because you really don't want to fire unless a human is telling you to fire. But it could also be true in cases that we're talking about. So if you had, for instance, if you had a few robots in different people's houses, maybe you have an operator that's sitting in the call center, and that person is just waiting for the robots to say, hey, I'm about to do something dangerous, is this okay? Or I'm about to do something really important, can you double check? You know, I'm bringing them their medication, can you just double check that these are the right pills? So we've been thinking a little bit about that. How can we better pull humans into the loop? And ideally, they will not be roboticists. Because in here, when the people sitting in the van looking at these different grasps, they were graduate students and professors. What we'd really like to do is have non-technical people be able to do this. So here's an example of an Aibo, this cute four-legged dog that's walking towards a ball. You know, so that's not too bad. That seems pretty straightforward. Here's what it looks like from the dog's view. So you can see it's a little bit noisier than you might expect. And the other thing you can notice is, at least at the beginning, you can see there are these dark regions. So because the camera's not all that great. So the robot has to deal with these different lighting. One of the things that helps here is the ball is orange, and it's relatively easy to identify orange on white and orange on green. Okay, so robotics can be hard, and one way you can do that, one way you can have robotics be successful is you have a really smart programmer who can think of all these things that could happen, and then try to hand code and prevent them. Another current method is something called learning from demonstration, where you can have a human teleoperate the robot, and then the robot tries to mimic it. So for instance, in 2011, I think, here is an example from Stanford where they had an expert go and fly a helicopter, do all these helicopter tricks, and then the program learned to mimic that human and do, for instance, upside down hovering, which is kind of cool. Another thing you could do is something called reinforcement learning. So if you had some kind of reward in the environment, you could try to maximize that reward. So for instance, here, these dogs are learning to go back and across the field, and their reward is the inverse of the time it takes them. So the faster they get across the field, the more reward they get. So what they can do is you just set these guys up and say, okay, start messing around with your parameters. So for instance, as the front leg is going, how high is the oval that describes that? Or how far out does the oval go before I touch the ground? So it can go and change these parameters, and then if it does something that seems to be helping, it'll do more of that. If it does something that seems to be hurting, it'll do less of that. So if you've got a reward, this environmental reward that's coming down, or it could be in a video game, it could be like the score, then you can do something like reinforcement learning. And the reason this is useful is, in this case, these Aibos were being used for the soccer game that I showed you, and they were able to use this autonomous technique to come up with a faster walk than anyone had developed at that time. So you had lots of grad students spending lots of hours trying to tweak their code to make the dogs walk faster, and it turns out the dogs learning how to do it on their own was actually better, came up with better results. So you can get better improvement. It takes a lot less human time because you don't have to have a human there turning the parameters, and it may take less time overall. So the one piece of technical stuff I wanted to go into a little bit of detail on today was talking about what if we have robots and we want them to learn, but there's no environmental reward. So if we bring a robot into someone's home and that person can't program, how can they teach the robot to do certain tasks? So if someone is limited mobility and you want to teach the robot when I drop something and say, help me, that it will pick it up for you. So, okay, we know that people can teach dogs, right? We have seeing eye dogs, hearing ear dogs. A couple years ago, I saw a a video of a dog that was actually driving a car. They were controlling the gas in the brake, but the dog was pretty cute. So dogs can do all kinds of things, and really you're just saying good dog and bad dog. So why not do this something similar with good robot and bad robot? So we can think and say, I've got some kind of history. So for instance, I could say sit, the dog could shake, and I would say bad dog. I could say sit, the dog would sit, and I would say good boy. And in a reinforcement learning setting, what you do is say, okay, this sequence was -1, and this sequence was +1. But what we were doing is saying it doesn't necessarily make sense to assign numerical rewards. We're trying to maximize the user's chances of giving us good boy, giving us good feedback. We're not necessarily trying to maximize some number. So what we did is, this is the one slide with math. We used a Bayesian framework. So what we're doing is we're saying, I've got some distribution over things, over policies. So there's some set of things I could be doing in the world. And then I've got some way of saying, what do I think the human wants me to do? And then I can maximize the chances that what I do would give me positive feedback from the human. So there's math. And then what's interesting though is, well, first of all, the trainers can make errors, right? Because we know humans are soft, squishy, suboptimal. We hit the wrong button sometime. So we got to account for that. The other thing is humans don't always say good dog and bad dog, right? When you're training your dog, sometimes you let it go for a while before you give it immediate feedback. And if nothing else, you need a chance to breathe every once in a while. So if the trainer thinks the dog did the right thing, it will give positive feedback with some percentage of the time and say nothing with some percentage of the time. If the trainer thinks the dog is incorrect, it'll give negative feedback with some percentage of the time and then say nothing. So what we'd really like to do is not assume these are balanced. So this is where we started talking a little bit with psychologists, and it turns out if you've trained a dog before, you might know that you're not really supposed to punish it. Turns out taking it and shoving its face in the poop, that's not a good idea. So you really want to give positive reward. You know, how could you hurt that how could you say no to that dog? And some people would train that way. There's also the case where, say for instance, you're 3 hours into grading, and really that student should just be happy you're not making a big red X. Because, you know, if the point is to make students feel bad about themselves on the test, you want to make those big red X's. Anyway, there are other cases where people not giving any feedback could be reward. So that was a hypothesis that we went out to Amazon's Mechanical Turk and tested. So here's an example where we have a dog, simulated dog, that's moving to one of the 4 corners of the field. The dog is trying to scare away the rats. In this case, the human trainer gives a positive feedback every time the dog does the right thing and says nothing otherwise. And what we found is the majority of our trainers gave reward when the dog did the right thing and said nothing when the dog did the wrong thing. However, a lot of people said good job when the dog did the right thing and said bad when the dog did the wrong thing. So we actually found evidence that people do teach differently. So our results show that if you can figure out what kind of person you're working with, you can learn faster. So, and the neat thing here is once you learn that, chances are it's not going to change too much. So if we bring a robot into someone's home, then we can learn about them, about what kind of trainer are you, and then use that for the life of the robot. So this is a very simple task where the dog just has to move in one direction. We could also think about, I'm going to skip to here. We can also think about sequential tasks. So for instance, here, move to the yellow room. The dog needs to move, that's not too bad. But then move the blue chair to the purple room. We have to teach the dog to push this chair all the way up here. And it turns out we can actually do that using the same techniques. It's just a larger planning space. So let me give you an example of this. Oh, the other thing I should mention is we looked at feedback to the human. So if the robot is really sure of what it's doing, it goes fast. If the robot's confused, it slows down.
In this demo, the agent moves at constant fast speed at first. The first task the user needs to train the agent to complete is moving the blue chair to the purple room. At first, we punish the agent since it moves to the green room without anything. Then it moves to the blue room without chair, so we punish it again. Then it starts to move the blue chair, so a reward is given. However, it stops at the green room, so another punishment is given. Finally, the agent moves to the purple room. Then we check whether the agent can successfully complete the command without any feedback based on last training. It shows that the agent reaches the goal state. Now we will experience another agent that moves at an adaptive speed. It adjusts its speed based on its confidence level's current action choice. Recall that the agent will still be trained in sensory environments presented in random order. The first task is moving the rat back to the blue room.
So here the agent's giving implicit feedback because it's moving slowly,
Unsure about its current action choice at the beginning.
giving the human a bunch of
But
chances
after
to give it
receiving
feedback.
several punishments for its incorrect behaviors, it moves faster. Then it becomes really sure about its current action choice and starts to move very quickly to the rat back. So some rewards are given. Finally, it successfully moves the rat back to the blue room. Then, when the agent executes the same command the second time, it moves faster at the beginning since it is more sure about its current action choice after last training.
So this is Bei Pong's dissertation work, and we're really focusing on virtual agents. But you could also think of training physical agents.
Before we begin, we will start with a high-level overview of the platform. Our TrillBot robot perceives the world using the RGB data from a Kinect cam. We do not make use of the depth channel. Using the RGB data, we design features for detecting the location of specifically colored objects in the environment. In this case, a pink ball and cylinder with an orange top. Perception data is streamed as fast as it can be processed, and every 33 milliseconds, the TurboBot must make a behavior selection from 1 of 5 choices based on the most recent.
So it's making a decision 3 times a second.
Are move forward, backwards, rotate clockwise or counterclockwise, and stay still. All of these behaviors run a fixed velocity for the full 33 millisecond cycle between decisions. By the agent selecting the same movement behavior as the previous one, it causes a smooth continual movement in that direction. To deliver reward and punishment to train the TurboBot, we use a Nintendo Wii controller, which allows us to give a +1, -1, or +4 reward signal. The +1 and -1 signals are associated with a short eligibility trace, so they primarily affect recent behaviors. Whereas the +4 signal is associated with a long eligibility trace to appraise a large history of behaviors. So we've placed an additional red circle over the video in the top left corner whenever punishments are being given, and a blue square whenever rewards are being given. Okay, let's get started with the high task. We begin by training the TurboBot to move away when the ball is close and in front of it. This involves putting the ball right in front of it and punishing it when it does the wrong behavior, and then adding a number of rewards when it does the correct behavior. Next, we give feedback to get the TurboBot to rotate when the ball is further away. Finally, we provide feedback so that the TurboBot stops when no signals is present. After this very short training period, the TurboBot has learned the correct responses to all the stimulus, and we can test it by putting the ball directly in front of it, which causes it to move away, turn when it's farther enough away, and then stop when the ball is out of its vision.
So I wanted to show that for a few reasons. First, the TurtleBot is one of the standard platforms, and it's one of the things that we have in my lab. So it can run around, and it does really well on hard floors, not as well on carpets. The other thing is, boy, that thing learns really fast. Now, okay, so part of it is, it could be because that was the guy who programmed the robot was the one training it. So one of the things we need to do is run more studies to understand, can normal people train a robot? How do normal people want to train a robot? Because if we're only developing techniques that are targeted at robotics experts, we're not going to be reaching the right population. So one of the things we're working on now, I just wanted to mention because I thought you might find cool, is the idea of curriculum design. So if you want a dog to do something really complex, you don't necessarily teach that complex task first. Instead, so if you want, there's one thing is called a blind retrieve. So you shoot the duck, and then the dog has to go out and grab the duck for you. But the dog doesn't know where the duck is, so you're yelling, go forward, go right, go left. So the dog needs to figure out what those commands mean relative to you. So it's got to figure out where you are. Okay, you're over there, so now I need to go over here. So this is a pretty difficult task, and it's a longer curriculum or sequence of tasks that you use to teach the dog to be able to basically be a voice-controlled dog, right? So then it's responding to you. So we've got some experiments showing that people, non-technical experts, can design these curricula that are useful for agents. So we're, again, going back to the virtual agents, because then we can use Amazon's Mechanical Turk to run a bunch of these experiments over the internet. Okay, so now I talked a lot about what I've been doing in terms of how do we get robots to learn what a human wants. Now, let's come back to what the course is actually about. How could robots be useful in the context of this class? So I'd like you to take 60 seconds, talk with the person next to you, try to come up with a bunch of ideas. Go. One of the things we've been talking about is the RAS, robot.
Activity support.
Thank you. I actually did forget the name, what it stood for. So RAS is one of the projects that one of the groups is helping on. And here we've got a turtle bot, and then we've got this mast. So now we can have, instead of, because a person isn't going to want to interact with the robot on the ground. So now the person can interact with something like the digital memory notebook, which I believe you talked a little bit about here. So a device that will help you remember daily activities. And now, instead of you trying to remember, okay, I took my medication, now I'm going to put it in the digital memory notebook. Now the robot can come up to you and say, you just took your medication, right? Now, one of the things that's kind of cool is we're saying this activity support is going to be in the context of a smart home. So now we've got all of these sensors that are around the house, and we also have the onboard sensors. So if the human, is doing something and you can't really see what's going on, maybe the robot could come over and get a better view. One of the other things we're talking about is, well, in most cases, we've got a caregiver. So we're thinking about, could that caregiver teach the robot? Could our robot learn watching the caregiver do an activity, and then we try to mimic it? So the caregiver shows us, okay, here's how you water the plants, and then the robot can know what that looks like. Either to do itself, which could be kind of hard, because it has a very, very small arm, and it's not very strong. Or, once the robot knows what successfully watering the plants looks like, then it can watch the human, and when the human does it correctly, doesn't say a thing, well, unless it's more like a pet and they're like, yay, good job. But then if the human waters 2 of the plants and doesn't water the 3rd, then the robot can step in and suggest, oh, here's a video showing how you usually water this 3rd plant. Remember. Okay, so mostly robots in the context of gerund technology are more a future technology. There's not a whole lot of practical applications right now. You'd be really hard pressed to go to Walmart and buy something, or even Amazon, and buy a robot that could do something useful for an older person. However, what I was trying to do today is show you that yes, robots is hard. Yes, we've been doing this for 50 years. But yes, we're also making progress, right? We're also to the point where we can get these robots to learn from non-technical people. We're getting robots that can almost drive cars. We're certainly getting drones that can do these really cool aerobatic tricks. So hopeful that this will come to fruition where we actually see some products come to market. And there are a ton of startups that are working on this stuff now. So trying to figure out, given the current level of robotic technology now, what could we bring to market in 6 months, in a year and a half, that would actually be able to justify their use based on the cost of that platform. So hopefully we will see more of these in the next few years. So we do right now have a few robot pets, interactive play with robot type things that have some intelligence. But hopefully the next few years we'll actually see some robots that are useful and maybe even eventually covered by insurance.